All right. I will begin with a word of prayer as I get up here. Dearly Father, we thank you for this day again. I thank you for this class and this opportunity we have to meet and study your creation. Just pray that you would guide our steps today. Help us to use this time wisely to prepare for the last test, Lord. In your name I pray, Lord Jesus. Amen. All right, so let's see here. Let me just look at quiz 6 with you guys right quick. So, you know, we were asked to show that V dual with G dual defined as such is a real geometry. So let's see here. So we need to show it's symmetric, bilinear, and non-degenerate. I saw some of you showed like symmetric and bilinear, but ignored the non-degenerate. It's not. That's a partial solution, but actually I don't know because you haven't turned this in yet. What am I talking about? But you know, except for one person. But sort of. But anyway, enough. Where was I? So this is the basis. This is the dual basis. If you don't like the upper indices and you'd like to use a different notation like F for the dual basis, you can do that. Like it's not written in stone, but that's the notation I'm going to use because I like it. Anyway, so the dual basis is defined by this relation extended linearly, right? And the metric upper components are defined to be the inverse components to the if we think of the matrix of G, the so-called Gramian matrix, the inverse to that matrix has components G upper IK. That defines this basically defines the G upper IK unambiguously, right? That makes them the inverse matrix to the metric matrix. Anyway, so with that, if we have a dual vector, the musical morphism, the sharp, we basically, in essence, raise the index of alpha by contracting it against the inverse matrix like this, inverse metric. So I've got sum over I and then sum over J. There's a typo in my notes here, so beware of that. Either here or the other place, but there's an error indice in there somewhere. As a general, let me shut up. So that's the definition of the sharp, and so I can prove a lemma, which is that the musical morphism is in fact linear if I have alpha and sigma dual vectors with components alpha sub I and sigma sub I respectively. Then, of course, the ith component of their sum is defined as such. And so if I take the sharp of this, then I have to contract the inverse metric against the ith component of the form, which is this. And when I use the properties of finite sums, I get that. Pull the constant out, and lo and behold, I've got C sharp alpha plus sharp sigma, which is to say it's linear. So that's essentially all I needed for the bilinearity, right? Because once you know that, then it's a simple matter to just go, okay, so if I take G dual, by definition, it's the sharp of C alpha 1 plus alpha 2, which is the C times sharp alpha 1 plus sharp alpha 2, comma, sharp beta. And then we are assuming that G is a metric, right? So I really should say going from here to here, take a point off my solution, because there really should be some comments over here like bilinearity of sharp, you know, and then going from here to here by the bilinearity of G, I can do this, right? And then definition of G dual for the final step. I usually put the qualifying statements over here, and me not doing that, you know, don't read too much into that. I'm just getting lazy. So I should take points off my solution here, right? I would like to see those kinds of comments for the best solution. All right, so anyway, and likewise, for the other entry, we can do this, right? And, but the thing is, I can flip, right? I can flip this by the symmetry of G, like that, and then I can use linearity of G, like that. So I'm skipped too many steps here. My bad. I must have been very sleepy when I wrote this, but Anyway, so there you've got linearity in the other component. And then, of course, symmetry follows pretty much immediately from, the symmetry of the metric, which, yeah. So, but why is it non-degenerate, right? Because we need to show non-degenerate to show that G dual is in fact metric. And so like I said, that's kind of just a calculation in my view. I'm sure there's another way to show this, but this is the way I showed it. So I calculate G dual acting on the dual basis, and after some calculation, right, so that's, I don't know, so what I'm doing here is a little bit sneaky. I'm rewriting the dual basis in terms of its components. Like the components to the kth dual vector are Kronecker delta ik. That's the ith component of the dual basis vector. So those are the components of it actually. And so I needed that in order to apply my definition of the sharp, which was, I contract the components of the vector against the inverse matrix, like so. And I threw some primed indices in here just to make it extra annoying, and also because I ran out of letters. And okay, great. So then after some moving things around and using my Kronecker deltas to squash the sum over A and the sum over B prime, of course leaves me sum over B and A prime left. I get this. Notice that there's a sum over A prime here. So if I rewrite that, oh, wait a minute, what'd I do? Oh, I kept these two. My bad. I kept these two. So I've got the B. There's different ways you could go here, but I went this way. So I kept these two guys together. And see that, by definition, is Kronecker delta K A prime, which then gives me this. And what happens? Well, all of this to say that the kth component of the dual metric is in fact the kth component of the inverse metric, which I find to be very satisfying. It's then immediately obvious that it's non-degenerate because the matrix of this metric is the inverse to the matrix of the given metric, which we're already knowing is invertible. So there are, I'm sure, other ways to do this calculation in terms of the fact that like the sharp is an isomorphism, and as such, if you were to look at the if you were just to look directly at the non-degeneracy condition in terms of the sharp being 0, you could use the fact that the sharp is only 0 for the 0 vector to get your pause on the needed non-degeneracy condition that way without actually doing this wonderful, glorious index calculation, which only I love. So you're like, I don't like this. You're like, well, yeah, that doesn't mean you're not a mathematician. That means you might be more of a mathematician than me, because mathematicians hate this stuff. This is just me. So, well, I don't know, some do. All right, well, anyway, I don't want to talk through all of the solutions, so at this point I'll just shut up and you guys have any questions and things you'd like me to look at in particular. Yeah.
Can you talk more about the Reitz vector? And you did go over it.
Yeah, the Reitz vector. So all the Reitz vector is where's that thing? Was that in here? That was. Where was I? Uh-oh.
General relativity.
Yeah, I was doing general relativity in physics today. For fun. This is the time of the semester I misbehave in physics, so. Was it in here that I had the...
It was in the quiz.
Oh, it was quiz?
Well, problem 85 in the mission had the Reitz.
Oh yeah, 85, that's what I wanted. Thank you. All right, so what is the Reitz vector? The Reitz vector is that y that we talked about back in like section, goodness, what was it, 6.2, 6.3? I can't. I'll have to open it up again, but in the textbook, to prove the existence of the adjoint, we prove that there exists a vector y such that if we have a dual vector, let's say alpha, the book says g, but I say alpha, such that alpha of x is equal to the inner product of x with this y. We prove that there is such a vector and it's unique. That vector is the Rietz vector. Now, in the context of the real geometry, the whole issue with the complex conjugation, the sesquilinearity of the inner product, the complex issue with the second component, that doesn't even play into, so we could even say alpha of x is like y comma x. It wouldn't matter if we're dealing with a real inner product because of the symmetry. But it is technically, it's the y that you need. The Rietz vector for alpha is the vector y such that alpha of x is equal to inner product of x with y. So here, the inner product of the Rietz vector of the trace, it's also what sharp is. The sharp is the Rietz vector. The musical morphism and the Rietz vector, these are the same thing. Yep. Mind blown, yes. You're like, wait a minute. All the monsters under my bed, they're the same monster, yes. It's true. Did I ever tell you guys, I was at Skate Estate, which was the place where it's kind of like the fun quest of my youth. And I was like, I think about maybe 7, 6, something like that. It was a birthday party. And like Michael Jackson's Thriller video. Just come out and they're playing this Thriller video on like this big projection screen at the Skate Estate. And it was terrifying because I was little. So I used to have nightmares that Michael Jackson was under my bed. In retrospect, that is a scary dream. But anyway. So yeah, that's the hashtag, oh I'm sorry, no hashtags. The sharp trace is the Rietz vector. It's whatever I need to take, x inner product, that vector is trace of x. And it's very silly in this case. Well, what's what's the inner product? The inner product was the inner product of A and B here is AB transpose, right? So the formula I need to solve is x times the transpose of the Rietz vector equals to the trace of x. Well, how can I make that happen? I just make it the identity matrix, right? So I didn't do a calculation here. I just did it's the identity matrix. Now you can always do a calculation, right? We've done that in other problems, yeah? Like let's look at another problem where we actually had to calculate it. Which was that? Which what? On the quiz, that was where it was? Where was that thing? This one's nice. This one's not bad, is it? Do you guys understand how to find the perp for column vectors? For the real case, you just calculate the null space of the transpose of the matrix of the generating set. That's something I teach in 221. And here, because the complex inner product has the complex conjugation, right? What it boils down to is to calculate the perp in like Cn. You just calculate the null space of you might say the adjoint of the matrix of S, which I mean by that to transpose each vector in here and take the complex conjugate of it. That how it works out. So that was kind of neat. But anyway, so this is that problem, wasn't it? No. Oh, this one's just fun. You guys like number 5? No? Yeah. Let's see here. Which number 7 do you guys say? This one was kind of fun. So number 7, it's like part A and part B. It's like, okay, this is stupid. I can calculate these all day long, right? Hooray! like, how do I get x1 minus 2x2 plus 4x3 from taking the dot product with a vector and the vector x1, x2, x3? Well, duh, right? I mean, like, there you go. I don't have a calculation for you. This is just by inspection, right? So if you ask me, well, how did you calculate that? I'd be like, I didn't, right? My brother joked about this. There's a professor at Bob Jones who taught there many, many, many years, Dr. Guthrie. And Bill saw him like sit in on somebody else's college algebra class once, or he's imagining it happening. Maybe it didn't happen, I don't know. But he's imagining, like, imagine he had to like sit in on this college algebra class. He'd be like, imagine him explaining the process of factoring. Like, there is no process of factoring for Dr. Guthrie. He just, polynomial, writes down the factorization, factored. It's like, well, explain that. I did, factored. You know, this is like that. So, and this one here, I mean, okay, fine. You got to be a little bit careful because of the, well, actually you don't. Like, this is the thing. This could have been way more interesting if it had involved I. It should have involved I. This is a bad book. This is a lost opportunity. It should have involved I so that I could see if you understood the I issue or not. As it stands, this is not a good example. But anyway, there it is. So like, again, I can just like look at it. I'm trying to solve this equals to that, so I'm just equating coefficients of z1, right? So I get like y1 bar equal to 1 and y2 bar equal to minus 2. I'm starting to show you a calculational method, right? Then I got to this problem. Whoa. Like, what just happened to me? Now, if one of you have figured out an easier way to do this, wonderful. I'm not saying that this is the only way. It's just the way I did it. So I'm trying to find the Reitz vector for what? For this dual vector alpha, right? And so what I need is that I need f with y to be equal to what? F of x, right? No, alpha of f, my bad. I need alpha of f, which is this, to be equal to f with y, whatever that y is. I don't know what the y is, but the context here is quadratic polynomials, right? So an arbitrary quadratic polynomial has the form what? Y naught plus y1x plus y2x squared. So I just decided to let f be ax squared plus bx plus c rather than trying to put in the details of f of 0 and f prime of 1 there. Excuse me. Anyway, so let me shut up. So I multiply this out. You got these 9 terms, right? You integrate them. And 9? 9. 9. And the integrations are all pretty easy because they're all monomials, you know, and they're integrating from 0 to 1. So these integrations aren't bad, and there's kind of a pattern, so all right, yay. But I need that to be equal to alpha of f, right? And alpha of f is f of 0 plus f prime of 1, which in our context, f of x being ax squared plus bx plus c, is this. So I need to solve c plus 2a plus b equal to that.
This is why we have row reduction.
Yes. So that means I need to, you know, equate coefficients of a with a, b with b, c with c, which is why I've got a 2, a 1, and a 1. And I get that. And then after some some solving, I get these from those equations. I plugged it into the calculator, you know, and that's what came out. And then I looked in the back of the book, and it also had this, and I was like, yay. So, yeah. Yeah. Oh yes, so the other way we could do this would be to use the musical morphism. See, if you could calculate, you know, if you could calculate the components of Gij, right? You could do sharp, what would sharp alpha be? you know, j equals 1 to 3, I guess, of alpha sub I v sub j, I guess, if I've remembered it right. So yeah, if I calculated, so, well, here's a question. Excuse me. I don't think actually we can calculate, we don't have to use an orthonormal basis for the musical morphisms. What'd I say?
So like, is orthogonal good enough?
I don't think we even need, my point is we don't need an orthogonal basis. Like we don't have to have, an orthogonal basis will make the metric diagonal. And that is very nice in terms of calculating the inverse of it. But the process of orthogonalizing polynomials is somewhat laborious. Like another path here is just to use the monomial basis. You know, you could just use 1x squared, and that would allow you to calculate the metric coefficients with respect to the monomial basis. So you could do like beta 1x squared, right? And then, so your gij, it's like the matrix with 1, 1, 1x, 1x squared, xx, xx squared, x squared, x squared. The rest are duplicates. And I can actually calculate those pretty quickly. What are the inner products here? We're using the 0 to 1 one, right? So we've got what? 1, 1/2, 1/3, 1/3, 1/4, 1/5, 1/2, 1/3, 1/4. You know, so that would be my metric matrix. And then you could invert this, right? You could take that and you could calculate the gij, and then you could use that. That's another calculational method. I don't think it's appreciably easier than what I did, though. Like there is an insurmountable, like someplace or another, you're solving 3 equations and 3 unknowns to do this one. It's just, it's baked into the cake of this problem, you know. I wish I had a homework problem which was kind of between, actually I think I did. I think the trace problem we just looked at is in between these two, right, in terms of difficulty. So, other questions? Yes, no, maybe so. Nothing? All right. Everyone's ready for the test? No? Yes? Excuse me. So I will, of course, post this. This last problem, I'm sorry about this one. Like I didn't make it interesting. So I made it diagonal on purpose because I was trying to not be mean. I was being nice to Gwyneth when this problem was originally given. You know, she was a good student. She asked me a question about whether or not the musical morphism would be on the test, and I said, well, sure. And so Gwyneth's problem was born. But what did you want to ask me about? The person who bequeathed this problem to you guys. A student of yesteryear. She's probably married with children at this point. I mean, I have no idea. I don't know where they went. I just see them and then they graduate, you know, and then you guys disappear. And I'm still here. I never graduate. Not usually, anyway. But so this one, the calculate the inverse components is really easy. It's 1 minus a half minus a third, right? Because to invert a diagonal matrix is just to reciprocate the diagonals. But you didn't even need to do that, right? Because this one, like to raise the lower index to the upper index, I used the metric components which are given. And so I just get that, and that. And then to check my answer, I calculate GVV, which is this times that, right? V transpose, the matrix, times V, which gives me that. But on the other hand, when I calculate the contravariant contracted against the covariant index, I also get the same thing, which, was what's supposed to happen. This would have been a better problem is if I'd given you the dual vector alpha, which would be AE1 plus BE2 plus CE3, right? These are the dual basis to the standard basis. In that case, we could have actually meaningfully raised the index, and it would have been exciting. So, because then we'd had to calculate the inverse components, which would cost us reciprocation, yay. And as such, we'd end up with like alpha upper 1 is A, alpha upper 2 would be minus 1/2 B, alpha upper 3 is minus 1/2 C, minus 1/3 C. And if we were to calculate G dual, right, on alpha alpha to connect back to that earlier homework problem, which would have made this a better problem, but the dual problem didn't exist in Gwyneth's generation of this course, I don't think. Or maybe I was just nicer then, I don't know. But G dual alpha alpha ends up being this, which, by the way, will work out to, I think, exactly the same thing again in terms of A, B, and C, but whatever. Maybe not, actually. Maybe that's... Oh, I guess that's going to be A squared minus 1/2 B squared minus 1/3 C squared, actually, for that one. Okay, anyway, I just wanted to talk about that momentarily. Let me show you something else here, if I can find it. So the bonus, I handed back the bonus thing to you guys, and I might ask a question on the test about some of the bonus material. If I did, it wouldn't be the really fancy stuff. It would probably just be something I'm talking about here right now. So I don't really have much to say about the proof of associativity. I think you guys are fine with that. Finding the multiplicative inverse is just solving, algebra element times algebra element equal to the identity. Nothing much to say there. This is more what I wanted to talk about, because some of you don't quite get this yet, and it's not hard is the thing. So the matrix representation of an algebra element, all I do is I look at the left multiplication map, right? And I calculate the components, the matrix of the left multiplication map with respect to the basis. If we're working with the standard basis, this is especially simple because all we do is simply calculate like A times E1, A times E2, A times En with respect to whatever algebraic structure we're dealing with. So like this one, it's the product algebra, which is this just says you multiply component times component. So like, let me write out what A times E1 looks like. A times E1 is A1, A2, AN times what? 1, 0, 0, right? And so what's that equal to is A1 and then everything 0. That's all that's going on here. It's nothing fancy at all, really. And so that's why I have this A with zeros here, right? So the standard matrix, how do you find the standard matrix? You act on E1 for the first column, E2 for the second column, and so forth, right? So here I do the same. I just, E1, E2, all the way out to En, and that gives me this. So this is the representation of the direct product algebra. It's kind of dumb. The one that's more interesting, perhaps. So this is just the isomorphism between the hyperbolic numbers and the direct product algebra. That's kind of more in the realm of like bonus kind of question. I don't want to talk about that so much. This is kind of more on point. Finding the regular representation of like multiplication in Cn. So here, multiplying n vectors and the complex numbers times themselves. When I do that, again, so this one I actually have to think about the basis because I'm not using the standard basis in this case. I'm using this E1, IE1, E2, IE2, da da da, EN, IEN basis for Cn. So I'm looking at Cn as a 2n dimensional real vector space, all right? And so that means I have to calculate the components of these vectors. Like LZX on E1, that gives me the, whatever the coordinate vector is of that, that gives me the, the components of the first column. And then I take, Z times IE1, that gives me whatever the coordinates of that gives me the second column. So when I do that, I get x1 plus y1 times e1. That's all that's left there, right? Everything else is 0. And so when I calculate, I've got x1 copies of e1. I've got y1 copies of e1. So that's because the first thing in the basis is e1 and the second thing in the basis is ie1. That's why I have this and this. Over here, I've got this ie1 because that's the second basis element. So when I multiply that by this, I get a minus on the y1 term, and I don't on that one, which is why I end up with this plus x1 times ie1, which is the second thing, and then minus y1 e1, which is the first thing in the basis. So this calculation is very much the same one we went through to understand the real Jordan form. These are real Jordan blocks. Every one of these, it's a direct sum of real Jordan blocks, is what this is, right? So that's one of the reasons I like to talk about this in here is because it gives us an interesting example of a matrix with a nice pattern, which ties into the larger story we've told in here. But anyway, so that's how that one went. The n hyperbolic numbers are more interesting because there you don't have a bunch of zeros. Like it stays mostly non-zero, right? So like left multiplication by z, E1 is the identity is the unit. So that makes whenever you have the whenever you have E1 is the identity for the algebra, the first thing in the regular representation is just the number you're representing. And then when I multiply by j, what does it do? I haven't written it down, but the last thing here would be like j to the n minus 1 times xn, right? When I multiply that by j, I get j to the n times xn, but j to the n is defined to be 1, which is why that moves up here. So anyway, it really is just looking at z, jz, j squared z, and so forth, and it just ends up it just keeps pushing the xn down pattern-wise, and you always end up with an x1 on the diagonal. That happens in other examples too, like the next one. Oh wait a minute, that is it. So I wanted to mention this because like most of you here tried the bonus, and not everybody, but and that's okay if you didn't. So I will publish these, so at least you have these to look at. But any questions? Let me close all my relativity tabs. We definitely don't need to look at the Schwarzschild metric today. I should open up my tensors though.
We've got 8 minutes left. We can do some relativistic physics, right? As long as you don't put it on the test.
No, I mean we can learn it on the test, right? It's a good place to That's the height of good pedagogy, is teaching people stuff on the test. That's what I learned in grad school. They're like, you need to teach students things on the test. I mean, students will get bored. If the test is just stuff they've seen before, they'll just be like, oh, this is so boring. You need to put new material on the test in order for the students to like feel alive.
How about new material as an extrapolation of old material? Where it's not the same sort of question as before, but it builds on those concepts.
let's talk about, let's see here. The idea of problem 90 and 91, I have made many a test question about those, but that question does tend to get asked more on the eigenvector part, but then again, anyway, if I've asked an emission problem about it, it's a potential test question. So this tensor business here, right? So here I define the tensor product of two vectors, right? You notice what I'm doing here? I'm really showing you a way we can look at vectors in an active way. See, because I'm letting the vector essentially act on a dual vector, aren't I? Now, how do you do that, though? You let the dual vector act on the vector is what you do. It's kind of funny. But anyway, I think this is a nice problem in terms of, I definitely should test on like bilinearity, right? And I should definitely test on, you know, what's a basis for bilinear forms, that kind of thing. So this problem has some of those elements. I like this one in that regard. I like this one too. You know, prove that upsilon serves as a basis for the the bilinear forms over V dual. So this is an extension of the last problem, right? So what do I do? So first of all, I think I show that if we look at a linear combination of these vectors, well, these tensor product of vectors in upsilon, if we set that equal to 0, a linear combination, if we evaluate on, oh man, some kind of spurious, I don't know what that is. We don't need to put a minus there for sure, right? So we just evaluate on that pair when we do that, right? When we take this and we operate on that, by definition, it's the sum of the constants of this object acting on those, right? And then by definition of the previous problem, this is the dual vector Vk acting on Vi and the dual vector Vl acting on Vj. But by definition of dual basis, this is Kronecker delta Aj and this is Kronecker delta Ki, which just selects for us CKL, which then proves that this is in fact linearly independent, right? So it's linearly independent. Does it span? Is it a spanning set, right? To prove it's a basis for the set of bilinear forms, I need that it's a linearly independent spanning set. So to prove spanning, I do that down here. So how do you prove spanning? We'll take an arbitrary element, an arbitrary bilinear form on V dual, right? And so I have to feed it alpha beta, and I do that. There's the component expansions of alpha and beta respective. So I can pull the components out, right? Then I've got this B, V upper I, V upper J here. That's just a number for every pair of indices I and J. And over here, I'm going back to basics, right? The ith component of alpha I is alpha of Vi. Remember this. When we looked about the things we learned about dual basis are still relevant. The dual basis, to calculate the ith component of the dual vector, we simply take the dual vector and operate on the ith vector, right? This is alpha I. This is beta J by our previous work in dual vectors. But then, that is also, understand, Vi tensor Vj acting on alpha beta by definition. So I can pull that out. Then I've got this map, right? This sum of these maps acting on this is equal to all that. But this and that hold for arbitrary alpha and beta, which shows you that B is actually equal to all this, which shows us that the span of upsilon is the whole kit and caboodle, right? It's everything. I took an arbitrary bilinear form on the dual space, and I showed that you can build any one of those from a span of these gadgets, right? Now I don't have to ask the question like this, right? I could ask the same question. What if instead of V dual I said find a basis for BV? What would you do then? what would the basis be for bilinear forms on V?
Tensor of alpha and beta.
Right. Well, yes, but instead of alpha and beta, like these guys, but instead of indices down, indices up, right? So like V upper I tensor V upper J would be, you know, the natural choice to make a basis there. Now, I'm much more likely to tell you to prove that that is a basis than I am to ask you to invent it yourself, all right? I understand the notation is certain encumbrance to you guys. So I'm very likely to tell you, prove this is a basis or something, right? But I'm just saying there's other versions of this problem that are reasonable to ask you. Would you like to see my current edition of the test? Let's see what I got. Let's see here. Here's where it currently stands.
White space provided.
Well, yeah, I mean, this is, I will add white space, and I will definitely not have all of these problems because, well, you know, yeah, you know. Let's see here. What's problem 1? Why is that there? Do you remember the quiz? So maybe I want to redeem myself from that quiz, you know? So that might happen. Prove or disprove. If S is a set of non-zero orthogonal vectors, then S is linearly independent. What word is here now? Non-zero. It's a different problem, isn't it? Yeah. So would you prove or disprove? Prove. Good choice. Prove the range, the perp of the range of the adjoint is the kernel of T. Prove, yeah, it is in the homework, exactly. Some of these are in homework. Some of these are like parts of propositions and sections in the chapter. This is the sections we covered in the book, right? Prove that the length of T of X is equal to the length of the adjoint of T acting on X, you know. Distinct eigenvalues give you perpendicular eigenvectors. If you have a self-adjoint linear transformation, the eigenvalues are real. Every one of these problems here, these are nice entry-level questions you guys should be able to really have a shot at solving, you know. There's nothing in here as sophisticated as, say, prove the adjoint exists, right? Now, Daniel has been lobbying me and trying to goad me into putting the question if W1 and W2, excuse me, to prove that W direct sum W perp is equal to the vector space in the case that V is finite dimensional. That's actually a decent test question. So I feel like I should tell you guys that as well, since otherwise Daniel has an unfair advantage if I was to put that on there. But to prove that, here's a quick sketch. Take a basis for W, right? Extend it to a basis for V. Gram-Schmidt on that basis, normalize the basis. Then you get a basis for your whole vector space. You can argue then, if you take a vector in the perp, it's necessary that the components of that vector are 0 with respect to the part of the basis which spans W. By the way, the Gram-Schmidt algorithm preserves spans, right? It goes vector by vector. Like the span of the first two things is the span of the first two things orthogonalized. The span of the first three things is the span of the first three things orthogonalized, and so forth, right? We know that structure for the Gram-Schmidt, and you can claim it in a proof. Okay, so so then you can argue that if Y is, you know, if you have a vector in the perp, it's necessarily the case that the components of that orthonormalized basis are all 0 with respect to the W part of the basis, which means that everything outside of the W part of the basis must serve as a spanning set for W perp, right? And then it's just counting, because you've got n minus k things in there, and you've got k things in the basis, so you've got n total things. All that remains to do is to prove that W plus W perp is, I mean, how do I know that the last n minus k vectors in the basis is linearly independent. I kind of sketched how do you prove it. It's a spanning set, but it's a subset. Anyway, we know a subset of a linearly independent set is linearly independent, right? So there's that. So then the other thing you need to prove, of course, is that like W1 plus W2 is, excuse me, my bad. W plus W perp is the whole vector space. How do you know that's the case? Well, remember we have a theorem that says that the dimension of W1 plus W2 is the dimension of W1 plus the dimension of W2 minus the dimension of the intersection, right? But you should have already proved that W intersect W perp is 0. And as such, the dimension of W plus W perp is the dimension of W plus the dimension of W perp. But that's an n-dimensional subspace of an n-dimensional space, therefore it's the whole space. Therefore, W plus W perp is V. All right. So that's what Daniel's trying to goad me into putting on the test. Yes?
How many nights of sleep would you lose if we proved that by contradiction?
Maybe I'll do your grade by contradiction. I don't know what that means. As you can see, then I want to make a question about, and then I've got these other ideas about questions which I'm trying to come up with, but then I realized that I need to solve my problems for my advanced analysis class, and then it ate my life. So I'm still distracted by that at the moment. But anyway, it's been a good semester so far, guys. I hope you guys do well on the test Wednesday. I think you can. I think everybody here could conceivably make an A. It's very much within striking distance for everybody. So.